In autonomous driving scenarios, maintaining globally consistent maps is crucial for successful operation. To address this, we propose a lidar-based localization and mapping system that leverages high-definition, HD, maps as prior information. Our technique extracts information from the drivable area and ground surface height components of HD maps to construct 4 degree of freedom, 4 DOF, pose priors. These pose priors are then integrated into the post-graph optimization problem to create a globally consistent 3D map. Maps play a central role in autonomous driving systems, particularly for localization and path planning. However, the accumulation of drift in the map and the estimate over time remains a critical issue. Traditional approaches, such as loop closure detection in GPS-based methods, have limitations. GPS signals can degrade in urban areas due to on-line of sight or multipath effects, while loop closure detection may not be feasible in scenarios without loops or with dynamic objects. Recent datasets, such as MCD and Hilti, provide dense survey-grade RGB dense prior maps, but these are not suitable for real-time SLAM due to their large size. In contrast, HD maps, like those in the ArgoVerse2 map change dataset, provide information about drivable areas, lanes, and road surface height as vector maps, which can be used to enhance the localization process by providing prior information about the environment. Our proposed system significantly improves the global consistency of the map compared to state-of-the-art lidar-only approaches, particularly in GPS-denied environments. This work serves as a first step towards long-term navigation of robots in familiar environments by updating the map. The proposed method leverages HD map components to enhance SLAM trajectory optimization and generate a globally consistent map aligned with global coordinates. Building upon a traditional lidar-based SLAM algorithm, it ensures accurate localization and mapping results for long-term applications. Key contributions include the construction of prior information for a SLAM algorithm from HD map components, the introduction of a post-graph optimization scheme with HD map-based factors, and the demonstration of higher accuracy compared to current state-of-the-art LOAM algorithms. The paper reviews related work in lidar-based SLAM algorithms, including advancements in LOAM and its extensions, direct methods, and the integration of IMU data. It also discusses the use of prior information in SLAM, such as loop closure constraints, GPS data, and roadmaps, highlighting limitations and the potential benefits of using HD map components as prior information. The proposed approach is particularly suited for challenging environments and does not require building structure information, making it a significant advancement in the field of autonomous driving and SLAM technology. The authors propose a comprehensive HD map data representation, comprising a lane graph with pedestrian crossings, a drivable area vector map, and a ground surface height raster map. This HD map data, available in the ArgoVerse2 TBV dataset, enhances the accuracy of traditional SLAM algorithms in challenging conditions, making them more suitable for real-world applications. The authors introduce notations used throughout the paper, including the HAT notation for estimates, Breve notation for measurements or priors, and the definition of the vehicle's pose as a tuple of position and orientation. The residual between two SE3 poses is also defined. The HD map is composed of a lane graph, pedestrian crossings, drivable area, and ground surface height, each represented as a vector map or raster map, providing 3D information about the environment. The problem statement is formulated as obtaining a globally consistent map via post-graph optimization with prior HD map constraints. The post-graph cost function is defined, which minimizes the difference between estimated poses and prior HDMA registered poses, as well as the relative pose between consecutive key frames from the SLAM process. The system overview consists of two main sections: the SLAM algorithm and the prior map constraint computation. Keyframe information from the SLAM algorithm is matched with the existing HD map, generating prior map constraints used for post-graph optimization. The SLAM algorithm, optimized from LOAM, is a critical component of the system. It utilizes a keyframe registration method and post-graph optimization thread that incorporates odometry constraints from the SLAM algorithm and prior map constraints. The global map is constructed after the complete trajectory has been optimized. The HD map to pose prior constraint consists of two components: the ground surface height map and the drivable area vector map. Preprocessing involves computing the prior map constraints by decomposing the keyframe's pose into yaw, pitch, roll, and translational components. The roll and pitch are preserved, while the yaw and x, y, z components are refined with the HD map. The Scanto map matching method estimates the prior map constraint from the road points of the keyframe point cloud and the drivable area vector map. This is achieved through the normal distributions transform, NDT, scan matching, which matches the keyframe road points with the HD map points via an optimization problem on SE2. The optimized 2D pose, psi asterisk operator, x asterisk operator, y asterisk operator, is used for constructing the 3D pose prior TM element of H. The altitude constraint estimation method utilizes the ground surface height map to provide a general representation of the road height. The HD map derived altitude is defined as ZGSHM, x, y, where GSHM is the ground surface height map function. Finally, the authors assemble the final HD map pose prior to be used in the post-graph optimization problem as follows: T equals R, T, R equals R, psi asterisk operator, R, theta, R, phi, T equals X asterisk operator, Y asterisk operator, Z asterisk operator. The paper introduces a novel method to enhance the accuracy of lidar-based simultaneous localization and mapping (SLAM) algorithms by integrating prior map constraints into the pose graph optimization process. The authors propose utilizing a custom factor derived from the noise model factor 1 class provided in GTSAM to enforce the constraints obtained from the prior map. They evaluate their method against three state-of-the-art lidar-based SLAM algorithms LOAM, LOAM, and DLO using the ArgVers2 TBV dataset. The experimental setup includes implementing the proposed method on the LOAM framework, downsampling the dataset to reduce the number of sequences, and performing all experiments on a desktop computer with an i7-12700 CPU. The results show a significant improvement in accuracy from the proposed pose graph optimization method, with an improvement of up to 45 cm in the RMSE value compared to ALOAM. The authors also provide a quantitative analysis of the performance of their method against the baseline algorithms, including mean, median, RMSE, standard deviation, and maximum error values. This paper highlights the potential of incorporating prior map constraints into SLAM algorithms to enhance their performance and provides insights into the design and implementation of such an approach. It is essential for researchers and developers working on autonomous driving and SLAM technologies to understand the benefits and limitations of this method and its implications for real-world applications. The authors conduct a comprehensive evaluation of their proposed approach, comparing its performance to three state-of-the-art lidar-based SLAM methods, DLO, LOAM, and ALOAM, across 208 sequences from the ArgVers2 TBV dataset. Figure 4 illustrates the distribution of root mean squared error, RMSE, values for each algorithm, revealing distinct differences in performance. DLO exhibits a large deviation in results, with high accuracy for some sequences but significant drops in performance for others. FLOAM performs slightly better than DLO, but still shows large variations, with a maximum error value exceeding 8 meters. ALOAM demonstrates better performance in terms of RMSE distribution, although its accuracy still deviates in several sequences, with a maximum error similar to FLOAM. In contrast, the proposed approach yields only one outlier with an error value above 1 meter, and for the majority of sequences, the RMSE value is less than 30 centimeters. A qualitative analysis is also conducted, examining the performance of each method for 10 sequences, as shown in Figure 5. In feature-rich environments, lidar-based SLAM algorithms perform well, and prior map optimization only slightly improves accuracy. However, in sequences D, F, G, and I, the proposed approach achieves significantly higher accuracy compared to baseline SLAM methods. The authors also discuss cases where their approach only improves accuracy to an extent, such as sequences A and H, and limitations of their system, As observed in sequences B and J, the primary reason for these limitations is the lack of information present in the drivable area vector map for these sequences. The proposed approach utilizes HD map components as prior information for generating constraints in pose graph optimization, building upon a typical lidar-based SLAM algorithm with keyframe registration strategy. This approach demonstrates highly accurate results in challenging scenarios where state-of-the-art lidar-based methods perform poorly. It appears that you've provided an incomplete transcript. Please provide the complete content, and I'll be happy to refine it according to the guidelines you specified.